So hi there, this is a lecture regarding mirrors, and of course the course is still optics, as everybody knows at this stage, I hope. So I will in this lecture introduce mirror as another type of an optical component that can be used for imaging. So please recall the previous lectures we have been mainly discussing of using lenses for doing imaging. And in here, we will do the same thing by basically just using mirrors. And before I progress forward, I would also point out that if you're really interested in the topic, this is actually a very broad and large topic. So a lot better information that I can provide will actually be handled to you if you start reading the book by Hecht and on optics. So basically the chapters regarding mirrors really provide a pretty good overview on the topic, and it's a far larger in scope that I can muster in this one single lecture. But what I will be doing in this simple lecture is that I will start by introducing
a simple flat mirror
as an optical component, and then I will progress to understand how a curved spherical mirrors behave. And please note, in Hecht they are also considering other types of curved mirrors, not just spherical ones. So please have a look on that material. The main motivation here of using mirrors and introducing them to image objects is that they can really used often to miniaturize your optical instrumentation. And perhaps one of the most important changes that we have compared to lenses and components based on optical materials, glasses, that they are dielectrics, is that now we can really reduce the chromatic aberrations because light is not really propagating through inside the mirror material, but rather is being just reflected. And in this reflection process, that doesn't really depend on the incident wavelength as such, so that it gives us a possibility of making more dispersion-free optical components. So this is the kind of main advantage, or one among the main advantages and changes that we have when we are using mirrors compared to using lenses. Of course, the price we pay is that the using of mirrors and designing things is actually by far from trivial. With lenses, designing things, optical instrumentation is usually easier, but as so many times in different topics, there's no free lunches anywhere. That if you want to design something that has better capabilities, then you need to compromise with the kind of performance and capabilities of others, or you have to spend a lot of more time in designing your actual instrumentation. But nevertheless, this was my short motivation on the actual lecture, and I will now boldly start by just starting with the actual main message I want to convey to you. So mirrors can be used also to guide light, exactly like lenses. And how it can also be done is that we can also form image objects, so that we can really use mirrors for imaging things. And what we will do next is that we will show how mirrors can actually do this feature, how we can image an object point into an image point. And we start by considering a flat mirror. And the behavior is exactly illustrated in the figures A and B. So we start by having an object point at the optical axis. That will be the object point here. And we are looking what happens when a ray of light is propagating into the flat surface of a mirror. Let's for example, imagine that this would be silver coated mirror. It could be a piece of a metal with a slight protection layer of reducing oxidation of the metal layer, and then the ray is being reflected and bounced here. And then what happens if that I would have an eye of an observer here, or I would have a camera and I would image, it would seem to be that the object point actually would be behind the mirror here at the image point. So this is basically what happens. So object at a distance of SO from the mirror is being imaged, and the ray propagates from the object, is being reflected by the mirror, and seems to be arriving from the point B. And because of this, that it seems to arrive from there, it's actually a virtual image that is being formed when I'm looking at the ray of light and how the object point will be imaged. And this is the distance of SI away from the mirror's other side, and basically the same kind of notation, the same equations that we have discovered for using lenses to do imaging still apply for the mirrors. So this is basically what we will be doing here, considering in the beginning of the lecture. So image formation, when we think about it, still it seems to be a simple process, but the trouble here is that when we are using mirrors, it's not exactly identical equivalent to the case that we imaged when we imaged using lenses. So, for example, when we would be considering a three-dimensional object point, and that would be highlighted in the figure B down below in the slide, then how the image actually looks to be, it's that it's not the original object anymore, but rather it's mirror image. And what I mean with this mirror image is that the handedness of my object will be changed. So basically, if I'm looking at these arrows, so that instead of like imaging a single point, I would actually have a collection of points, making my object three-dimensional. So basically, that's what I'm trying to highlight with these different arrows. I have my arrow pointing from the original center of object towards some kind of distance along the z-axis, the optical axis. Then I have the other extensions of my object that I want to image. And here on the other side, how this kind of object looks like, it's actually not exactly the same object anymore, but rather it's mirror image. What I'm trying to say here, I do not remember if I'm explicitly mentioning this at home. Yes, I have. So try this out at home. Look at your left hand through a mirror. Like it can be what kind of mirror you have at your home, but anywhere you have, look at how the left hand looks like. And then when you look at the mirror image of that, actually looks to be your right hand. And this is exactly what I mean, that the handedness of the object changes when we are imaging through the mirror. And this is actually, even though it seems to be just a curiosity, this actually matters quite a bit. So that sometimes this is actually a huge change in the kind of imaging properties. So for example, the images, they might flip along the y-axis and x-axis, and then when you're using mirrors, you have to be really careful of the overall image process. So this is actually something that you should pay attention to. And now we have gone through a kind of the concept of a flat mirror and how it behaves. Please note that it seems to form an image. It's a virtual image, so rather instead of the image being formed into a real point, it's actually a virtual point. So it only seems that the rays of light will be converging into a point, but there's actually no real center point where the rays are originating at the mirror. At the image plane. And now let's consider next the behavior of spherical mirrors. That's another kind of basic type of a mirrors. And let's consider a radius of curvature of r into our case. And let's consider that we still have an object point at the optical axis that will be denoted with a capital O. And then that will be again at the distance of SO against from the mirror surface. So this will be my object point, and my radius of curvature should be here. My object point, I have this weirdly noted. So this bar corresponds to the distance into the capital O, the focal plane, and then it's this length bar that gives me the distance between the surface of the mirror and my object point. And then C denotes the center of the radius of curvature that is being forming the mirror. So that will be the radius of curvature denoting here the distance, and then I will have my image point at the distance of SI, and this will be my image point denoted here in the figure. At least I was confused with the figure myself, so maybe you are also, so that's why I spent that time. So, reflection angle of the ray that originates from my object point, now of course depends on the location at which the ray reflects from the mirror, so that the things become slightly more complicated. But on the other hand, we do recall the reflection law, so that the reflection law states that the incident angle here on this interface will be the same angle as the reflection angle. So the calculation is basically trivial. The only complication that we have is that we need to somehow calculate how the local plane of incidence actually lies with respect to the angle and with respect to the ray that is propagating here. So this is where the kind of magic happens in terms of the ray tracing software, that these kind of configurations can be easily calculated using computers. But if you want to do it by hand, it's not very easy, because of course you would need to do vector calculations. So you'd basically need to kind of define your ray of light, what is the angle here, and then with respect to this, you need to define the plane, and then you need to use you probably want to define the plane using a surface normal, because then you can define the plane, the local interface, using a vector product against the plane and the surface normal. But we don't go there, but in case you're interested, you would know how to do the calculations. Nothing bad, just the application of vectors into a geometrical problem. Now the image forms at a point I, as I mentioned, and the distance again will be denoted with SI, and this fulfills the lens equation, so the imaging equation. So we still can use the 1 over SO plus 1 over SI equals the inverse of my focal length. So this would be the lens power, or here basically the mirror power. The only thing we must do here is that we replace the focal length F with the radius of curvature, and this applies for a spherical mirror, so that the F equals minus R over 2. So once we place this into here, we can really use the lens equation, imaging equation, and then we can apply that to the case of spherical mirrors. Please be extra careful with the sign conventions when you're using a mirror. That is usually where the mistakes happen, so that you have to be really careful. And this is the kind of the kind of most cumbersome thing for you to kind of work out. And it might be also troubling, because I guess we don't have that good intuition anymore when we are kind of trying to imagine how a curved mirror images things. With lenses, it's somewhat easier, but when we want to understand how a curved mirror behaves, then we usually start lacking a good practical understanding of things. But maybe you could try it at home. Maybe you have a spoon at home, so that you're also sometimes eating something with a spoon instead of a fork and knife, or chopsticks. Is that then you can see how your face looks when you're imaging it through the spoon, and then you can change the curvature of your mirror quite easily by just rotating the spoon smartly with respect to your hand. So then you can even see yourself how the image formation will change when you change the radius of curvature from a positive to a negative 1. So I really recommend you to try that at home. Spoons are nice, incidentally, by the way. You can also get singularities out, so that if you're interested in kind of like a work of Sir Michael Berry, he was doing and still is doing amazing stuff regarding geometrical optics back in the days. So that there you can actually see formation of caustics using mirrors. So that I would say it's pretty cool stuff. Just using something that you can find from your home. Okay, back to the topic. The transverse magnification of lenses and similarly the mirrors will be exactly as we have encountered before. So that you please read mirror here and not a lens here. So the transverse magnification is again defined that it's the size of my image with respect to the size of my object. The trouble here is that when we are imaging something that is not a point light, then we start really quickly introducing aberrations in mirrors and with spherical mirrors, so that things become complicated quite quickly because of the configuration. The greatest advantage, like I already mentioned in the motivation of using mirrors, is that this behavior of them reflection doesn't really depend on the wavelength. So there's no refraction, no light is propagating inside the material, like with the case of lenses. And this means that the wavelength of incident light doesn't really matter into the image formation process. So basically, please recall reflection law. There's nothing in the reflection law saying anything about the refractive indices of the medium. It just states theta I equals theta R. And then we have the refraction law, the lens equations, and Snell's law. Then we have the refractive indices there inside the equation. So compare refraction law, the Snell's law, Ni times sine of theta I equals Nt times sine of theta t, and the reflection law. And that kind of tells you mathematically what I'm trying to say here. So that they're basically dispersion-free components. And this is quite nice. If you would use lenses, for example, to perform imaging, many times they start being restricted by aberrations. And many times, if you're just using single lenses and not many lenses together, joined together, then you start also having chromatic aberrations. And these are basically color aberrations. So a color of light giving rise to an image, for example, at the red color, it will form an image slightly differently than, for example, blue light will form, and that introduces a kind of blurriness into your image where the blue colors and the red colors start to be a little bit separated. And this is known as a chromatic aberration, and we can easily see this on our own when we are using a single lens to do imaging and of colorful objects. So at the kind of outer rims of things, you start seeing more red usually than blue, due to the fact that the lens has normal dispersion, so that the refractive index profile is such that the refractive index, in other way of saying the lens power, is stronger at the blue wavelengths. So this is one advantage. And in practice also, it's way easier to manufacture really large mirrors than lenses. So if you really want to make a kind of conventional lenses, they become very bulky, heavy, and polishing them into the right type of a surface profile becomes very demanding. So if you want to do very large optical components of the size of a meter scale or even more, then using mirrors will be way easier. And the nice thing is also that you can make actually quite lightweight, large mirrors that you wouldn't be able to do with normal lenses. Of course, Fresnel lenses would be a topic that you could really use to make reduce the weight of a huge lens, but nevertheless, this is not practical when you go even larger and larger sizes of optical instrumentation. So basically, space telescopes, that's a prime example. They're all based on mirrors and very large mirrors, and they are not using lenses as such. So mirrors you can use also to miniaturize instrumentation, so that you can also just shrink down the size of your optical instrument if you design things using mirrors. And this is many times taking place in company work, that they start by prototyping a device, they check that it works using normal lenses, and then when they're finally making a product, they want to sometimes make it as small as possible and as lightweight as possible and compact. So then they are, instead of using lenses, they are using mirrors, and they are letting some kind of expert to design their prototype using mirrors. So this is also a very common feat that is done with the companies, so that it allows to reduce the weight, it will make things easier, and that will be the benefit of doing this hassle of designing something more complicated. Fresnel lens, I would like to point out this as an example, even though it's not actually a mirror, but at least you can heavily reduce the weight of your optical instrumentation if you're smart. So please Google what's a Fresnel lens. It's in a kind of a lens discovered by Fresnel and designed, where instead of the kind of lens shape being a conventional, a kind of a convex surface, it's rather a kind of changed profile, and that allows to make thinner lenses. And at the time when this invention was being made, lighthouses were still in use, and they were actively guiding ships on the right passage during the night time, and this was actually a huge thing. So Fresnel lenses at the time, they probably saved millions of lives of sailors, or at least thousands of sailor lives, because they were effectively the lenses that they were used to help making lighthouses. So if ever you go to a marine museum somewhere around the globe, it might be that you will have some kind of Fresnel lenses there in place, showing of this history of sailing of mankind. At least in the kind of marine museums I've been in Finland, there has been Fresnel lenses on show to kind of show this, and they're a pretty cool piece of instrumentation, I would say. They're huge optical lenses of the size of tens of centimeters, and they look really nice. So this was all. Thank you for joining me, and please join me shortly on my next lecture, where I will be going through
Prisms.